In this presentation, we will discuss how we can use the frequency response function method to describe a multiple input, multiple output system. So let's start with considering this general shaped structure, and let us suppose that it is excited with a complex force, like this. And let's suppose that we measure the velocity, the complex velocity, in the same point 1. So if the system now is linear, then we know that the responding complex velocity, vibration velocity, can be written as the product of the exciting force with the frequency response function connecting the excitation in point 1 with the response in point 1. So index 1, 1 denotes this connection with excitation 1 and response 1. So if we expand this frequency response function in its magnitude, the absolute value, and its phase factor, the response will look like this. If we introduce a second point, point 2, where we measure the vibration velocity, we will in the same way obtain the response as the product with the second frequency response function and the exciting force, and so on. So if we have m response measurement points, we obtain this column here with response components, response velocity components, and as you can see here we have a column vector with frequency response functions h11 to hm1 and a single exciting force f1. So if we now introduce a second complex force with exactly the same frequency as the first one, and let us now assume that this second force excites the system in point 2. If now the system is linear, then we know that the principle of superposition holds, and then we can write the total response due to both forces in point 1 as the sum of two contributions. The first one, where the excitation force F1 is connected to the response component via the frequency response function H11, and the second one in an analogous way with the frequency response function connecting the excitation in point 2 with the response in point 1. And then, of course, one can go on in an analogous way and write all, the contributions, the total response in all m points in this way. And as we can see now, we can organize this as a multiplication then, where you obtain the response vector, m by 1 response vector, by multiplying the m by 1 frequency response function vector with the m by 2 frequency response function matrix with the 2 by 1 excitation force vector. So this system is characterized with the m by 2 frequency response function matrix. If we generalize this to a system where we consider m points, the response in m points, and if we apply exciting forces in n points, we can represent this system with a frequency response function matrix that is an m by n complex valued matrix. So this frequency response function matrix connects or couples an n by 1 excitation force vector to an m by 1 velocity response vector. So, as I said, this frequency response function matrix is, of course, as usual, complex valued and frequency dependent. And also, it is a system property. So the values of this, the numerical values of the components, is dependent only on the properties of the system itself. It is not in any way dependent on the excitation force properties.